So last time I did go through chapter 4, and in the end there was very quickly a bit of this about the frequency evaluation. I'll say a bit more about that, and then also a bit more about the comparison between frequentist statistics and Bayesian statistics. The big difference is, of course, that in Bayesian theory, there's both these epistemic and aleatory probabilities, while in frequentist definition of probability allows only this aleatory probability, always just as a frequency of some infinite repetitions. These frequency evaluations are, however, also useful in Bayesian statistics in a way that to understand what are these, if we repeatedly use these approaches, how they behave in that. But there's a difference in the way that in frequency statistics it's more important to define also these estimators that they fulfill certain frequency properties, while in Bayesian inference it's just enough that we can check afterwards that the Bayesian approach is also somewhat sensible with these frequency properties. And so there was this few terms I also mentioned last time. I just recap. Asymptotic consistency is that if we get infinite amount of data, then the uncertainty should vanish. Our posterior should go to a point, and if it happens that there's a true model, then also that point would go to true parameter value, and if there's no true model, it would go to that parameter value, which given that model, the predictive distribution would be as close to true data generating distribution as possible, measured with KL divergence. And this can be shown that this is true. Easier to prove it for parametric models where the number of parameters doesn't increase, but these have been also proved for non-parametric models where the number of parameters increase with the amount of data. Unbiasedness, that if we repeatedly make some prediction, or guess, estimate, and then we compare it to the true value, and then when we repeat many, many times, we can look how this, our estimate, also in a finite case, how that estimate differs from the true value, and if we compute then average over repeated experiments, it's unbiased if average of that error is 0. In frequency statistics, often the estimators have been derived so that the first most important thing is to have unbiased estimate. The problem is that this can be actually sometimes leading even silly results. For example, there are cases where for absolutely positive value, unbiased estimate can be negative. It's possible to show, yes, if you now take the average over the errors, you have on expectation 0 error, but then in order to get that unbiasedness, it requires that you sometimes make a negative guess for something you know that is positive. It's not that important in Bayesian inference. It's more important that the combination of possible bias and then the variability would be small. So small error overall is more important. And it's quite usual that when we use priors, those reduce the variance of the estimate. But it's quite unlikely that we would get guess priors that would be exactly the same as what nature is. But even if we are there somewhere there, we can reduce the variance of the estimates a lot, but still the bias can be quite small, and so we get smaller errors overall. Efficiency, in some idealized cases, it's even possible to show that Bayes estimates are optimally efficient, but of course these assume then that, for example, our prior guesses would be these matching the true nature. And then it gets more complicated that what if we are just close to optimal priors. Traditionally, efficiency is measured with squared error, but of course we could think about overall, given other utility cost functions also, that how good estimates we can get, and then of course we can then optimize also how do we make these guesses, decisions, if we also optimize based on these specific utility cost functions. Calibration. So alpha posterior interval has the true value in alpha percentage cases, and it would be calibrated. In frequentist statistics, it's common that starting from that, how do we come up with confidence interval that would be calibrated? And in Bayesian inference, again, we do the Bayesian inference as usual, have a model prior combined with data, and it's not kind of the necessary that we would have perfect calibration. We did discuss when doing model checking, these posterior predictive checking approaches are looking at some kind of calibration. But it doesn't need to be perfect, and it's usually that you get good calibration if you have good models. It's also in a way that if we don't stick that, we would have perfect calibration. We can get also possibly shorter intervals in a way that we are able to predict more accurately something. And then if it's not exactly. Kind of the example of very bad interval which would have perfect calibration would be such that in 5% cases, we would say that true value is, let's say, pi, and in 95% of cases, the interval would be from minus infinity to infinity. Now, in 95% of cases, the true value would be in the interval, and for any practical estimation, in 5% cases, the true value would not be in the interval, and this would be perfectly calibrated confidence interval, but of course not sensible. So we would prefer to get sensible intervals. O'Hagan-Forster Bayesian inference book has some additional examples of problems with unbiased estimates and these kind of strictly calibrated intervals. So in frequentist statistics, it's only then these aleatory probabilities. And so there's some way that you have data, and from the data you can compute somehow estimate. And uncertainty in that estimate is then considered only what if we would have seen some other data? What if we would repeat the experiment and see different data sets? And so in that way, the inference is based on data we did not observe. We require, for example, the unbiasedness and the calibration, the behavior, they come from thinking that what other data we might have seen if we would know, again, the true data generating mechanism. There's also, in a way, it's common to say just Bayesian versus frequentist, but actually frequentist statistics has different schools also how to make these estimates. Maximum likelihood is one of these kind of that not accepting that we would call combining the likelihood and prior to posterior, just looking at the likelihood. And that fulfills just these asymptotic frequency properties, but not necessarily unbiasedness. And then there are estimates which then would start from requiring unbiasedness, and given unbiasedness, then thinking about additional like minimum variance or calibration of confidence intervals. And then I already mentioned that requirement starting with this unbiasedness may lead to high variance or even silly estimates. So unbiased estimate for strictly positive parameter can be negative. And I also talked about these, that these intervals derived just based on calibration requirement doesn't need to be sensible. The difference also now in Bayesian inference, the interval, we can say that our epistemic uncertainty is that the true value is with some probability in this interval. In frequentist confidence interval, you can't say that. You can only say, again, based on the aleatoric uncertainty, that if we repeat the experiment many times, then in certain proportion that interval includes the true value, and in other cases doesn't. But for any specific case, it doesn't allow saying that what would be the probability that it's in that interval, because it's epistemic comment about the epistemic uncertainty. There's a great amount of very useful frequentist statistics. There's a lot of kind of things that kind of between that people who might at some point use frequentist statistics can make also very useful models and think about useful properties and so on. And then it might be just at some part, and sometimes it's kind of not that sensible, like having these negative estimates for positive parameters. Also for simple models and a lot of data, there's not much difference. Laplace did use Bayesian approach already before Bayes. He used it for astronomical data. In the beginning of Laplace's career, there was not much astronomical observations available. He had to be able to make inference with small amount of noisy observations, and he then used prior information. During Laplace's career, there started to be so much astronomical observations that in the end he also did actually use frequentist approaches, just because kind of the uncertainties were much easier at that point with lots of data and the models stayed simple. So in a way that there's no kind of the reason for just bashing frequentists. Even the Bayes approach offers a lot of kind of the improvement, but you can also learn a lot from the frequentist literature. And the benefits are then that it's easier for complex hierarchical models. It's natural how we can make higher levels, the exchangeability of the parameters, adding prior information. It's easier when model changes because we don't need to think about how do we derive the unbiased estimate. It's just using the Bayes rule. Now with the probabilistic programming, also the computation is easy. And there's a consistent way to add prior information if that is available, which it's changing that at some point when there was a lot of arguments between frequentist and Bayesian, Bayesians wanted to also be so that Bayesians can be objective and try to make inference with as little prior information as possible. But now it's more and more accepted that it's sensible to use all the prior information you have, that it's kind of I just can't remember the English word, but it's kind of bad that if you would just throw away useful information. A lot of machine learning, it's not pure frequentist or Bayesian, so in a way that it's not just these two probabilistic schools. There's a lot of very pragmatic approaches, picking whatever works, and then somewhere there between. Then about hypothesis testing. This has been asked also during the lectures. And kind of specifically now talking about the null hypothesis testing. So that assuming that there would be some null hypothesis, for example, treatment effect, the treatment effect is 0 or non-zero. And then treatment effect being 0 would be this null hypothesis. In the course, and in the book, the teaching has been that just show the full posterior distribution. That there hasn't been much comments about hypothesis testing. In the exercises, there has been this kind of discussions comparing, for example, hierarchical model and pooled model, which is related to hypothesis testing, or looking at the kind of how big these effects are. This null hypothesis testing, it's me and others think that it's kind of being too much emphasized and kind of ignoring then the information we learned and then making it just binary decision and reporting only that binary result. It's kind of throwing away information and hiding information from the communication. Some Bayesians have been then following that, okay, kind of that we have to be able to do the same thing, and they are also into null hypothesis testing, and still there is a lot of papers coming out how to do this null hypothesis testing. It can be in some cases sensible, but then quite many think that also that it's in too many cases forcing of this, and I have some kind of illustration of this. frequentist null hypothesis testing asks what if data is generated from the smaller model, and then kind of can the actually observed test statistic, can it be kind of that what if we would generate from the smaller model, would we observe that kind of test statistic too? Kind of bit related to what also like the posterior predictive checking, there was test statistic for actual data and test statistic for posterior predictive. But then in this case, instead, just looking at the kind of assuming then that somehow we can then reject the model. And now the problem has been just that then it's too often interpreted that if we reject some model, then the alternative would be the somehow sensible model. So it doesn't tell whether the more complex model is actually good enough. So I don't say anything more about the frequentist, and now I just go about the kind of the different ways Bayesian hypothesis testing has been made. Instead of hypothesis testing, we recommend that instead report full posterior. So this is the beta blocker example from the book, and it's been used also before illustrate computation, and showing the odds ratio. So it's showing that there's less deaths in the treatment group, and showing the full posterior distribution is more informative than just answering the question that is this treatment effect different from 0, and if the treatment effect would be 0, then the odds ratio would be 1. We can see that there's a lot of posterior mass saying that the treatment is beneficial. It can be actually highly beneficial because the odds ratio, the posterior distribution goes almost to 0.3. There's still some uncertainty also that, okay, there's small probability that it might be actually harmful, even increasing these strokes, and then but still showing this whole information is better. And then there could be utility or cost function, there could be then decision that whether we need more data. Just since this is now continuous parameter, it's not sensible from the continuous distribution to ask this question that what's the probability that treatment effect is 0 and odds ratio is 1, because for continuous distribution, probability for one value is then 0. So we need to do something else if we want to then think about the hypothesis testing. One way would be just look at think about what is the probability that we have that we know the sign in which direction this is. Is this treatment beneficial? And now this says that, okay, it's a 99% probability that the treatment is beneficial. It doesn't say anything about the magnitude, but it says that 99% beneficial. This could be also one way then to summarize the posterior information. But even then it's useful to also show the full posterior because we could have the same case that it's less than 1 but very narrow near 1, so that we could be very confident also that it's still very small, that treatment effect. Now it also shows that it can be actually quite big, this treatment effect. Some people then like to compare whether the posterior interval includes this null case. So here's 95% its interval, and then they would say that, okay, now this is, the treatment effect is not zero because the null value is not included in this interval. This is again changing it to just binary value, yes or no inside the interval, and then kind of arbitrary decision that which interval was chosen. So I would prefer this one. This is still continuous value we are reporting, and in a way that we are not choosing yet in this phase that whether this is big enough probability or not. Here we first have been choosing how long interval we choose, and then decide whether it's looked at whether null is included. We can also improve in that way that I also already mentioned that case that maybe the treatment effect is useful, but it's very, very small. And there's this region of practical equivalence. If we have some additional information saying that how big treatment effect there should be before we would make the effort to implement, to start manufacturing some drug or recommending that it's used to treat patients. And then we could, here this is just, I don't know what would be reasonable interval for this beta blocker case. So I've just showed some for illustration that we could say that anything inside this interval is not interesting for us. And then we can compute that what's the probability that we are outside of that interval. Of course, more kind of the refined version of this would be actually to have for different effect sizes also some utility or cost, and also compute also like the expected utility, that what would be the expected number of saved lives if we would use this. And that would also then take into account that actually there's a small probability that it's harmful. So some people then use kind of are able to have enough additional information that they can define these regions of practical equivalence, compute probabilities whether inside or outside of that. And then there are also some who kind of combine this posterior interval and the region of practical equivalence. And now instead of looking at whether the interval includes just the null, whether it overlaps with that region of practical equivalence. I think it has the kind of the similar problem as when computing null. Of course, a bit more conservative, but still changing it to that we are choosing now two things: interval, the region, how wide the region of practical equivalence is, and arbitrary some percentage for the interval, and then answering yes/no question.
So you have to publish your whole distribution. Otherwise, there's always a risk that the reader will miss some information if you don't publish this whole. Data.
Yeah. So the best would be that you could also publish data, so that people could also then check that what if they would use different prior, what if they would use different model, and so on. But even if, in a way, sometimes data is sensitive, but then it would be good that you could publish as complete information about the full posterior distribution as possible. Because in even those cases, if you publish as much information about the posterior, they could also check just that what if they change the prior, how sensitive that posterior is to prior. Of course, it gets more complicated when we go to hierarchical models that you would need to actually publish then the model and the posterior draws. But that is something that, so publishing posterior draws happens rarely, but it's something that at least is discussed that should happen more often. Kind of sharing sensitive information about the sensitive data sets, sharing them between different parties by sharing also the posterior draws. So here's an illustration now that also that in this case the original data was such that it seemed like that there's support that the treatment is effective, and then I just made also posterior where there's the observed data is such that there was same proportion of this in both treatment and control group who died, just to kind of illustrate some things how these look like. Again, reminding that with the continuous distribution, if we just compare whether it's exactly 0, the treatment effect, the probability is 0, so we need to do something else. We can compare that can we infer the sign, and you can see now that then here the probability would be closer to 0.5. We could compute the interval and look whether the null is included in the interval. We could make this region of practical equivalence. You can now see even with this relatively narrow region, the probability does change, that we are not that certain that it would not be in that interval. And we can do also this combination whether it would be region of practical equivalence combined with the posterior interval. Here's an alternative comparison then, that now these both are cases where the observed proportion is almost the same. Another difference is then that another data set has much more observations, and then again kind of comparing how these look like. So can we detect the sign? They are kind of the similar results. Is null included in the interval? Similar results. But here it's quite different, that even if the kind of the probability of detecting kind of inferring whether we can know the sign, there's a quite big difference. That here we also are very certain that it's not harmful. It's unlikely to be useful and it's unlikely to be harmful. Here, there's still a possibility that it might be useful, but it's also a possibility that it could be harmful. So clearly, showing the full posterior is more information than just that probability. Here, saying whether that interval includes null, in addition, showing the full posterior gives us more information. For the region of practical equivalence, big difference in this probability whether it's inside that interval or not. But again, showing the full distribution is useful. And the combination here. Here, there's a difference now that the interval is actually inside the region of practical equivalence. So it could be inferred that we have also kind of very strong information that nothing interesting to see, but it was also possible to see also here that probability that this would be outside of the region was very small. So overall, yeah, it might be sometimes useful. I think these kind of the intervals are mostly useful if you need to solve many posterior distributions. It might save space. Even then, I would prefer some kind of density estimate, showing also the shape. You can also fit many of the density estimates in small space. Intervals might be useful in text, that if you need to summarize something in text, but in a figure, so a histogram or density estimate. Base factor was discussed briefly in chapter 7. Here are some examples for this the same case. Now it has the specific that it's assuming that this odds ratio 1, treatment effect 0, has non-zero probability, that there's a non-zero probability that it can be exactly this. For something like beta blockers, where it's, I think it's more likely that with that kind of drug there would be always zero probability that it would be exactly something. Like homeopathic drugs is example where I would assume that yes, there's also the non-zero probability that the effect is exactly zero. There are other cases where we can think of this that there would be also for the zero effect non-zero probability, but I think that these kind of the cases are minority. So now, if we then say that there's a non-zero probability of zero treatment effect or ratio 1, we need to also make then posterior inference for that null model. What would be the posterior inference if we assume that? And what would be in this beta blocker case, we had two groups, and so we would still be inferring what's the common probability of dying, assuming that the groups doesn't have difference. There's the bridge sampling package, which can be also used with STAN. In the bridge sampling, because STAN can work, MCMC can work with this unnormalized posterior distribution. We don't know these normalization terms, and then when we are comparing the null model and treatment effect model, we want to integrate out the parameters of those models and just compare the marginal likelihoods of these models, but they need to be normalized. We need to, or the marginal likelihood corresponds to normalization term of these each posterior distribution. Bridge sampling can do that by having some known distribution like Gaussian distribution, and then using several steps of importance sampling to figure out the normalization term also for posterior obtained from STAN. So we can get this then like base factor based probability that what would be the probability that the effect is exactly 0. I've shown it here. So it's saying that kind of that it doesn't know. But just showing this that it doesn't know is not that informative if we would not show that posterior distribution at all. Again, showing the whole posterior tells us that actually, even if we don't know whether treatment effect is non-zero, there's quite big probability that it's a big effect. These Bayes factor-based approaches, they can be prior sensitive. Now I just use default priors, so you might get different results using different priors. And that's also, I think, one downside of these computations. Here's that what if the observed data has similar frequencies in both groups. We get higher probability that odds ratio would be 1, but it's still ignoring a lot how much uncertainty we have that it actually there's a quite high probability that it's saying that there's a high probability that it would be not beneficial but also not harmful. But looking at the whole posterior distribution, this is something that we should not recommend people to eat just like that, because it could be also harmful at this state. So without giving kind of the permission to sell this as harmless, we would need to also actually study more that this is not harmful. So I think that this is kind of giving too high probability for the null model. And here's then with the more data, and you can see that it's giving higher probability for the null model now. In the course, I did advertise then, and the chapter 7 discussed using cross-validation. And then that is related to overall looking at the predictive performance. And you compared models that can, hierarchical model, for example, give us better predictions. So we could also then, in these kind of cases, compare what if we have a model where treatment effect is fixed to 0, and what if it's unknown? Can we predict better with the model which we have this unknown non-zero treatment effect? It also requires then that we make the posterior inference for the null model and the bigger model, or projection from the full to null, which was part of the extra material related to the chapter 7. And if the posterior parameters are independent in the posterior, it's actually better to look just the posterior directly. Especially the cross-validation, it has a high variance because we are there cautious in a way that we don't trust our model, and we say that we are reusing the observed data to simulate future data, and that part is making it that it has a high variance and kind of the model-based looking at the posterior, if we trust our model, is then more informative. Of course, we need to make all the model checkings before we can trust the model, and cross-validation can be part of that model checking too. In beta blockers example, leave one group out is not sensible, as there are only two groups. It's difficult to then predict for the other one. Leave one person works out, and then there's this case study showing that it's less efficient than looking at the posterior. In this simple example, we can trust this model. This illustrates quickly the simulation experiments. On different lines, there's the how big is the true odds ratio. So I fixed the true odds ratio at these different levels, and then I simulated 100 times data. And so the observed data could have then actually different odds ratio than what was the kind of the based on simulating, and that gives the variability there. Here, if we look at the posterior distribution of then the odds ratio, we can see that if the odds ratio, true odds ratio is 1, we get uniform distribution for the probability that the odds is below 1. Then that's sensible. It's well calibrated model then. When the odds ratio gets smaller and smaller, we can see that the probability that odds is below 1 is in more and more of these 100 repeated simulation close to 1. And so, and around there, like treatment effect 0.6 and smaller, we odds ratio 0.6 or smaller, we are quite easily find that yes, this we can detect the sign and it's beneficial. The marginal likelihood comparison, there's a difference that when it's kind of favoring that when the odds ratio is close to 1, it's saying that, okay, there's nothing interesting to see, and these probabilities for having non-zero effect are close to 0, and then there's some transition and at some point saying that, okay, odds ratio is away from 1. But it's not as sensitive as just looking at the posterior. You can see that we need smaller odds ratio further away from 1 before it's certain. And in the same way, leave one out comparison is also, you can see this, it requires to go to smaller of these odds ratios further away from 1, so bigger treatment effects before it can see differences. There's a difference now between then the marginal likelihood comparison and cross-validation in a way that specifically the marginal likelihood comparison in these uncertain cases like to favor the null, while like the cross-validation has a wider distribution, and then eventually they all go over there. In the beta blocker, there was just the one treatment parameter. There's no posterior dependency. And then looking at the marginals and this, whether it's overlapping with null or region of practical equivalence, is difficult with many parameters. This is the body fat example. And now we see that weight and height, for example, both they are overlapping 0. But if we look at the bivariate marginal of weight and height, we see that the 0 is not inside this highest posterior density region. And it's difficult then to look at these in higher dimensions. We could do still
kind of parameter selection, or in hierarchical models to understand that all of the groups are kind of correctly predicted in some way based on how wide the posterior is.
Yes, so you can learn from the marginals something, but it's just that if you have the dependencies, then it gets difficult. And then, of course, you could also then check that do you have high posterior correlations and so on. And in a way here, there's also, it's kind of, here you can see a difference in a way that some of the posteriors are narrow and near overlapping with 0, and then the weight is wide and overlapping 0. That's also kind of hint that it's likely to be actually dependent with some other parameters, and it's dependent with many parameters in this case. So we could then use like Bayes factor or cross validation in this kind of case where we have posterior dependencies, but you can see again that it's a bit problematic, just that both of them are in favor of removing weight from the full model having all the covariates, but at the same time, if we instead start with the small model, they are both in favor in adding weight. And this is because just given abdomen, the weight has additional information, but given all the other variables, weight can be excluded because all the other variables contain similar information. So this is then complicated, and then, of course, I recommend this projection predictive variable selection I discussed more on lecture 9.3, which can order the variables easy and tell you how many variables you should pick and so on. Okay. Final slide on this hypothesis testing, that you may have heard about these typical hypothesis testings, t-test, pair t-test, Pearson correlation, ANOVA, and so on. And they are all just linear models. And you can see that you could use R-ARM, for example, or BRMS easily to make these. But instead of just doing that binary test, you can easily get the full posterior distribution and learn more. Here, this GID is group ID, and so you have there, for example, the last equation then showing the hierarchical model where there's kind of additional intercept term for each group. And of course, we can also then extend these with group-specific variances, different distributions such as T or Poisson distribution to make them more easy, and in a way that you don't need to think about that, what is the name of certain distribution I should use now. You just think about how do I model my data, and then you look at the posterior distribution, and it's easy to make changes based on what you know about your phenomenon. There's a nice longer list illustration of these tests as linear models, and just with LM, so using maximum likelihood, but you can just change each LM to stan underscore GLM, and also in our forthcoming regression other stories book, there's good discussion of this. We have now a break. After that, we have guest presentation about the using Stan in a company, and then after that, I will briefly also go through what's in chapter 8 and 14 to 18 and 21. So kind of that reading instructions for those chapters on, so there's the modeling, accounting for data collection, linear models, Gaussian processes, briefly on those. But let's have now 5-minute break.